okay? So before the break, we did away with the ultraviolet catastrophe. Now we're going to make away with another catastrophe with the same assumption. Essentially, it's a little bit building on the same assumption. So we're going to discuss the Bohr atom. But I thought we'll start with the same sort of setup as previously, and that is why this was such an issue for classical physics in the first place. So there were some experiments, Rutherford and other, which essentially determined that you had some sort of a charged particle in the middle, and then you had some sort of electron around, and then when they scattered off, the total size of this system was about an angstrom, okay? But the nuclei was much, much smaller, which meant that atoms were essentially mostly consisted of empty space. So the question was then, well, how is this kept together? Why do we have atoms in our daily life? Because if this is just here, then of course the Coulomb force will make the electron here just immediately fall into the proton. So the idea, the natural idea, well, perhaps this is sort of like in gravitation, like in the planetary system, right? That it orbits around, okay? And if it orbits around, then, yeah, we have the Coulomb force, right? Which in our units is E squared divided by R squared. But we also have the centripetal acceleration then, which is just V squared divided by R. So then Newton 2 just gives you E squared divided by R squared equals 2m, mass of the electron, V squared divided by R, right? Or if you again take it with the mechanics analogy, then we had that like V squared divided V squared times R, right? Is in this case constant, which here is just a E squared divided by me. And then, as you know, it also precedes in orbital mechanics that you can set up the angular momentum, mvr, which is then another constant which can take any value. So you have the two constants of the motion. Now, the thing, of course, that when we put this in this case, we know that since this is orbiting now, it's actually accelerating. The velocity vector is changing. And we have just spent a whole week on discussing what happens to an accelerating electron. It emits radiation. So this one would emit radiation here, according to our Larmor formula. So it will lose energy, and then, of course, it will start to spiral in and eventually end up as a proton. So again, we wouldn't have atoms like we do have them then. Or perhaps we would, because of course it depends on the time scale, right? Perhaps this time scale by which it radiates and then spirals in is 10 times the age of the universe, which back then wasn't known. But anyway, so it doesn't matter, right? So we can actually now estimate which time scale this should happen upon. So again then, we use our Larmor's formula, which is 2/3. I have to always remind myself here, c cubed a squared. And then this again, like before the break, this is just the total energy, the time minus the time derivative of the total energy, minus here because we're emitting, so we're losing energy, right? So in this case, what's the total energy of the system? Well, that's again the kinetic energy plus the potential one. In this case, the kinetic energy, of course, is mv MeV squared. The kinetic is just the Coulomb potential. So this, but then we can use this formula to write this in instead of here. We have this, so that's just E squared divided by 2, right? So that would be E squared divided by 2R minus E squared 2. So this is just then minus E squared divided by 2R, which is just, you know, U divided by 2, right? As we know. And then we can do this, hopefully. The V dt we can write as dV dr, dr dt, where we can calculate dV dr from there, right? Which is going to come out as E squared divided by 2 R squared, and then dr dt, okay? And that is now going to be minus then the Larmor formula, E squared c cubed, and then for the acceleration, well, we have our centripetal acceleration there, right? So we could just replace our centripetal acceleration with this expression there. That would be then E squared. So if we take the square, that would be E4 divided by ME squared, and then I think we're going to find like an R squared there, so it will be R4 there. Okay, so now we have a nice, simple differential equation here that we can solve for T and R, right? So let's say we're interested now, how long time does this take? So we take it from T equals to 0 to some T equals to, say, T0. Yeah? And R, we start from some initial radius, which here would just be this one, right, R0. And then we're interested in that when does it reach the nuclei at essentially 0. So we do this. There is only one dt there on the dr here. We're going to have to deal with some stuff. Can put the minus sign here on this side. Then we have the E2, and we have like an E6 here, so it's going to be 1 over E4 there. We have some various constants. Suppose it's going to be a 3 divided by 4. We have a C cubed, which comes upstairs, and an ME squared, which also comes upstairs, right? And how many R's? We have R4 there, R2, so we have the integral then from R goes to R0 to 0 of R squared dr. And this is then just the integral. On the other side, well, that integral is trivial, so we don't have to bother about that. And then, yeah, if we do this, we have R cubed coming out, right? So we see that the time estimate here for this to happen is going to be 3 divided by 3, so 4 C cubed ME squared divided by E4, and then R0 cubed. And now we could just plug in the constants. We could use our lecture notes, the back, and plug in and see what time estimates this would be. And then we would see, is it big or is it large? I will just because, you know, this is how I normally relate these things. We can do an order of magnitude estimate by using our Thomson cross-section. We can make contact to that, because that one we know, because we use it in so many applications in our course, that we know its value by heart, right? It's 6.65 times 10 to the minus 25 centimeters squared. So we can just rewrite this in a form that is essentially C4 up, ME, E, and then we have 8 pi divided by 12. I'm going to have a C4 and then a C in the denominator. We're going to have a 8 pi divided by then 4, 3 sigma Thomson. Pardon for that. We had a C up here, right? And then R0 cubed. So if we look at the order of magnitudes here, this will be 10 to the 25, right? Now the C is in the denominator. So this would be 10 to the 25. This would be 10 to the minus 10. Now I'm dealing with our CDS units, okay? And then the radius that we started, that's the typical radius of the atom, which we know is on the order of an angstrom. That's 10 to the minus 8, right? So that's 10 times 10 to the minus 24. So in this case, you see that what comes out is on the order of 10 to the minus 9 seconds. So the prediction here from classical physics is that there should be no world. We shouldn't be having these type of atoms that we have around because they should all collapse on the time scale of a nanosecond. So again, the order of magnitude estimate here is not to give a precise, right? That's to give the scale. This is not the time scale of the universe. This is not even the time scale of a few years. This is the time scale of nanoseconds that this should happen. So again, something was fundamentally very wrong here. Because we knew, of course, or people back then knew that, you know, atoms were stable in certain configurations. We also knew that they didn't emit continuous light from this process, but rather these spectral lines of varying strength, by the way. So this predicts that it should be a continuous spectrum just spiraling in. So what to do here? Well, then we have the Bohr hypothesis. Now, the Bohr hypothesis builds on the Planck hypothesis that we had before the break, when we did away with the ultraviolet catastrophe. So here we said, okay, we still have this one here. But then we say, okay, the atoms can only be stable if they exist in an orbit that has the integer number of Planck's constant divided by 2 pi, which normally then we put as n h bar. H bar is just the Planck's constant divided by 2 pi. It's to get rid of some notational there. And only when the electron is on these orbits, as we're called in Planck's hypothesis, yeah, it can be stable. And when it's stable, it doesn't emit electromagnetism. So it can just go around there. Yeah? And when it emits radiation, it's in discrete steps of energies h nu, right? And we had. And those then can make it from one state to another. And then when it ends up in the other state, then it's again stable. But that can only be with the integers here. Otherwise, it's not. So, yeah, then you have suddenly two equations with two unknowns, R and V, for a given n. So it's just again then a little exercise for you to show that the stable configurations are just given by these here. Now, so that's nice, but we were interested also in the energies, right? And in the wavelengths that the emitted spectra would have, given then by h nu, hc divided by lambda. So if we then now again take that this energy then, it's just the total energy, we had that before, remember, it was just minus E squared divided by 2 Rn, so that was just half the potential energy, yeah? And then we just use that to plug in these results. We get that the energy is minus E squared 2 there I am h bar squared, and then we get an E4 there, ME, and then we have 1 over n squared. And this now goes under R1 n squared, where R1 equals to, did I do an algebraic mistake? I'm going to see, E4 ME divided by 2h bar squared. Was that what I got? Yes, sir. 2.2 times 10 to the minus 11 ergs, or since we're in the atomic scale now, we often use the atomic measure of energy in electron volts. 13.6 electron volts. This is then called the Rydberg constant after the person who found it experimentally. So what can we do with that now? Well, we can predict the spectral lines and where they lie for this Bohr atom, which in this configuration, of course, we know now is hydrogen, 1 plus, 1 minus. So let's go about and do that. We have this formula for the energy, right? R1 divided by n squared, where n squared is the states. And we know that R1 is 13.6 electron volts. So we can look at some cases. So here we now have a lower and an upper. Okay? Now we're interested in what's the delta E between the upper and the lower. Well, we said that must be then minus 13.6 electron volt divided by n upper squared minus 13.6 electron volt divided by NL upper. So if we now put that as minus 13.6 electron volt, or 1R, and then we can write 1 divided by Nu squared minus 1 divided by NL squared. Okay? So then we can also say, okay, that's the energies predicted. Often we also want the wavelengths, right? We know that the energy is hc divided by lambda. So the wavelengths then, UL, is going to be, the energy is hc divided by lambda. So this must be then hc divided by delta E U L. So let's look at some. Which one did I take? I took the example where the upper is 3. Remember, they have to be integers. The lower is 2. Okay? We plug that in, then we get that delta U equals to minus 13.6 electron volts. We have 1 divided by 9 minus 1 divided by 4. This will come out as 1.89 electron volts. We plug that into lambda UL, and this will come out then as 6,561 angstrom. Do we know which spectral line this is? What have we done now? We have calculated the wavelength for a very specific spectral line, which we often use in astrophysical applications. Let's just say it like that. Yes. Hydrogen, and specifically hydrogen Balmer alpha, H alpha for short. This is the H alpha spectral line. Where does it lie? This we know. Does it lie in the X-rays? In the visible, indeed. Very good. This lies in the visible. Yeah? So we can observe it, for example, from the ground, towards the red in the visible. Yeah? But still, we can. We can, for example, we have some students now doing some observations of the H alpha line in some stars that my research group is interested in, and for that we're using our own Mercator telescope, which is situated in La Palma. Yeah? It's an optical telescope. So let's do another one. NL equals to 1, NU equals to 2. Okay? Well, delta, it proceeds exactly the same. Delta EUL equals to yada, yada, yada. And lambda UL will come out then. I'll leave you to fill in the blanks. These are some exercises for you to do. Will come out as 1216 angstrom. Which line is this? Do we know? This is hydrogen Lyman alpha. Lyman alpha. Where does this lie? In the ultraviolet. Thank you. This we cannot observe from the ground. We have to shoot off our telescopes in space, like the Hubble Space Telescope could observe this in the ultraviolet from local galaxies. Now, of course, the most recent famous space telescope, the Webb, It actually observes in the infrared, not in the ultraviolet. Hydrogen Lyman alpha is a very important line for a lot. However, one of the specialities that it has is actually to look at galaxies that are very, very far away at the beginning of the universe. The thing is that when we do applications later in the course, we will learn how photons get redshifted by the cosmological redshift as they travel. So light that were originally from these galaxies emitted in the ultraviolet might be shifted all the way to the optical or infrared here. And then Webb is ideal to examine those in the infrared. Now, of course, it also has other purposes, and that is that, for example, if you have like a star, and then you have a little object around it, like this, and then perhaps in certain phases, starlight then grazes the atmosphere here of this orbiting object around this star, then it can graze the atmosphere, creating a transmission spectrum. Now, because of the temperature of this object, think about again the black body, right? This might also then, in the local universe, emit a lot in the infrared, which also then Webb is very designed to observe in. This is, of course, then an exoplanet that I'm talking about here. Yeah. But that was a detour. Now, let's go back to our hydrogen Bohr atom, right? We can also do a lot of other fun things with this. One thing is that, okay, but what if now we want to get rid of the electron? Yeah? And we're in the ground state. What does that represent here? Well, then we have NL equals to 1, but Nu goes toward infinity, right? That and then we just plug that into, we can just look there, right? Then delta E for that is just 13.6 electron volt. Now, this is then the ionization potential of hydrogen from the ground state, right? This is how much energy it takes for a photon to come in to get rid of the electron, if the electron is in the ground state. If you have a photon coming in with less energy than this, that is higher wavelength than 912 angstrom, which is the ionization limit, it won't have enough energy to ionize it if it's in the ground state. And this has very important consequences because it created these edges, you know. We call this like the Lyman edge or the Lyman limit. Because if you have a photon that is of shorter wavelengths, there's higher energy, then this doesn't behave exactly like the line transitions. Remember the line transitions, you have to tune your photons exactly at this to get an H-alpha line photon, right? We calculated the typical width and it was ridiculously low, 10 to the minus 4 angstroms, natural width. There are other broadening mechanisms which we will discuss later on in the course, but they're very narrow, so you have to be very precise in order to absorb. But here, you can be a little bit less precise, but only on one side. Essentially, the cross-section goes something like this, and then it's just a poof, because all photons of higher wavelengths, of lower energies, they can never ionize, right? But those of higher can. And this creates very important effects. Like I said, the Lyman edge in various galaxies. We also have the Balmer edge, which you should now realize what it is. The Balmer edge is that, well, if you have a lower state that is number 2, and you want to ionize it, so to infinity, then you just plug in 2 here, so you get this divided by 4, right? And then you get the so-called Balmer edge for ionization. And that is because it's a very good temperature estimate of stars, for example, and we'll come back to that again later on, how that works. But you can see, hopefully, the, so to say, regularities here. We have the series, we have the Lyman series, which is everything from like 1 to 2, 1 to 3, and so forth, all the way to the ionization edge. We have the Balmer series, that is like 2 to 3. That's the alpha Balmer alpha, Lyman alpha, 2 to 4, that's the H beta, Balmer beta, or H beta there, 1 to 3, and so forth, 2 to 5, up to 2 to infinity, which is then the Balmer edge. If you put in 3 here, it goes by the name of passion, and so forth. And you see the regularity, the Lyman series, they're all in the ultraviolet. That's the smallest energy, that's the biggest. And they're all in the ultraviolet. These are all in calculate the Balmer edge and you will see where it is, right? But these are at higher, and these will of course be at higher wavelengths still. Yeah? So you can directly see the regularity and by this identify where they are in the spectra. So the thing with the Bohr atom is that it gave very good match with observations of hydrogen, right? And also actually with what we call hydrogen-like atoms. That is heavier atoms that have lost all electrons except for one. So think about a helium atom, yeah? And then you have 2 protons in the core, and you have lost one, so you have only 1, right? So that's like a hydrogen atom. However, instead of having just 1 charge in the middle, you have 2. So you have to modify the charge here. It comes with like a nuclear charge c squared there. Yeah? So if you do that, then for these hydrogen-like atoms, the Bohr theory also gives you for the wavelengths good results. But of course it fails for more complicated atoms. And that's where we have to appeal to real, if we call it that, quantum mechanical calculations. Now, in view of that, I wanted to, though, finalize today by making that little teaser, because remember the Bohr atom, it was actually based on this, again, peculiar ansatz, right? MVR, which had this NH bar, which was NH divided by 2 pi. Okay? Building on Planck, but still, okay? That's like the angular momentum is there now. So, but what if now particles also, like photons, exhibit wave-like behavior? What if we could associate wavelengths with also particles, like the electron here? Yeah? So that nowadays is called the Broglie wavelength. And it goes something like this. We know for a photon, yeah, we have the energy, it's h nu divided by c, it's hc divided by lambda, we have the p is e divided by c or h divided by lambda, momentum. What if we could now also do this for particles, that is, that they had wave-like character? So we take and call this the Broglie wavelength now, and then that wavelength is just h divided by the momentum by the particle now, like this. But that is just h mv. Okay? And then we say that for stability, we have to have standing waves. That is, we have our circumference in this case, and we need to fit the standing wave on this, which I'm going to draw very bad like this, with n nodes, and that's when it can be stable. So of course the circumference here will be 2 pi r, and that have to be then n times the wavelength, where n is the number of nodes here, okay? Compare it to the analogy which you might have seen. Well, if we pull like a, if we have like a string here, right? And then we attach it in the wall, and then you stand and you shake it up and down, then you know that there are certain modes, right, that you can create standing waves. So if I shake it with a certain frequency, certain wavelength, yeah, then we will have like 1 mode or 2 modes or an overtone. And if I shake it with the wrong, it's just a mess. Okay? So that's the analogy here. Now, in this case, let's go back to what this means then. Well, if we then have mvr, actually we can do it like this. It's easier, because we had the de Broglie wavelength here. So if this is then the Broglie wavelength, this is just n, what is it? H divided by mv. So what is this? Well, mvr equals 2 nh divided by 2 pi nh bar. So this ansatz is equivalent to the Bohr hypothesis. And this is indeed how you come up with the hypothesis that particles also have wave-like characters. It leads to exactly the same result. Okay. That's it for today. And on Friday, we're going to delve deeper into this, and we're also going to have a look at some real blast from the past.